This isn't the first series about the microcontroller matter, but I'm planning to make it a bit different by adding some more interesting peripherals and by having it built on circuit boards instead of breadboards. I can't not mention the video series of Ben either. You should stop this video right now and check it out if you haven't done it so far. This colleague of mine kept talking about it and kept sending me these video links, and I just couldn't find time to watch them. Then, while browsing around on Instructables, I found this other guy who made an 8-bit full adder with integrated circuits. And I thought to myself, that's a great idea. Very educational, using discrete components, and it's really working. So I decided to read the whole Instructable and found a link to Ben Eater's videos again. And I just couldn't believe it. I don't really remember which one of them it was, but the thing was already built and the topic was, I think, microcode. I watched that and binge watched about 20 other episodes, but within minutes I knew that I had to build it. So I looked around to see what I had lying around in my hobby shop and gathered a couple of ICs to begin working on the project. The company where I work was moving to another building at the time, and we got a ton of old electronic stuff that just got thrown away. There was this immense wood crate full of stuff, and I immediately noticed some through-hole boards with logic gates and decided to salvage some. And then I decided to salvage them all. And within an hour I got my hands on a box full of PCBs, many of which later turned out to come from an old IEF Werner PLC. That meant that PCBs were on deck and I began designing right away. Fast forward a couple of days or weeks and here we are. At the moment some parts are already built while the others are in the making, but we're going to start with simple stuff like transistors, resistors, LEDs, buttons. Then, like a dung beetle, we're going to roll all the stuff we build and learn into a microcontroller capable of running code. And of course, this microcontroller we build is not going to be in the same league of those made by TI or Microchip or whatever, but it will be more than adequate to present how awesome this microfield is. So without further ado, let's just get the dung rolling, the transistor. In its simplest form, we could think of the transistor as a switch. There are many types of transistors. I'm going to use a simple NPN bipolar junction transistor in my demo circuits. NPN transistors will turn on when subjected to certain conditions, and I'm going to show you how one can control current flowing on the collector by manipulating the current flowing into the base. Check out this small circuit. Increasing the current flowing into the base results in an increasing collector current. Amplifiers can be built using this property because the collector current is much larger than the base current. Let's see what happens if I feed a sine wave into the base. So let's turn on our power supply and then our generator. Wow, that's quite great, but we're going to use our transistors in saturation. That means that I'm going to either supply no current or I'm going to supply a current large enough to turn the transistor completely on. And we are going to use the transistors to build logic gates, and two known states are exactly what we need. We're going to use these do-it-yourself logic gates to build flip-flops, and we're going to use the do-it-yourself flip-flops to build a lot of different stuff. But as we prove how one can be built from the other, we're going to substitute these do-it-yourself versions with actual chips made by TI, onsemi, or whatever. We could run the numbers to see exactly how many transistors we would need to create a 4-bit counter, for example, but that's pretty much as far as I will go with this scalability thing. So let's see what the transistors are good for. This is a small board that I made. It's not that small actually. But its purpose is to demonstrate how a logic gate can be built from transistors. And if you look it up, there are several circuits on the web that you could copy, but you must be careful since not all of them work. And even though I had my doubts when I saw some of the schematics, when I thought, well, they're online, so I guess they must be okay. And it turns out that not all of them were. So, these black fellas right here, they are our transistors. And these are BC547, just like the other one from the little circuit I showed you earlier. And they are used to build 7 types of logic gates. There is an inverter, a buffer, an AND, NAND, OR, NOR, and XOR. You see those little buttons are connected to the inputs, and there are some LEDs around here so we can see when they're actually pressed. The blue LEDs are connected to the gate outputs, so we can actually see what's going on the inputs while taking a look at the outputs. I'm sure most of you guys have seen this before, but here it goes. The inverter gates output the exact opposite of what the input is. The buffer gate repeats the input. You need both of the inputs to be active in order to turn on the output for the AND gate. You need the exact opposite to turn off the NAND gate. You can have any of the inputs turned on to have the output turned on for the OR gate. Again, the exact opposite for the NOR gate, and the XOR gate will be turned on if the two inputs are not the same. See, if I press both, the LED goes out. Some of these gates have an additional very important property. The NOR and the NAND gate can be used to substitute for any of the other gates, including the inverter gate. This makes them far superior to the others, as you can have an array of NAND or NOR gates and configure them to shape anything you want, really, to a certain limits. You can create any combinational logic on a single chip. You can make decoders, encoders, latches, edge detectors, counters, magnitude comparators, and a lot more. In order to have a higher degree of visibility, I won't build stuff with a gate array of this sort, but I will rather build things from discrete components. Let's see what I decided to begin with. It's clear that in order to build a microcontroller, we're going to need all sorts of components, and one of the many is the memory. The simplest circuit made of logic gate that remembers previous states is a flip-flop. It has a data and a clock input, and it has two outputs, Q and inverted Q. The behavior is simple. The output Q will store the value of the data, or D input, when a rising edge is seen on the clock input. It looks like we finally have our excuse to take this out of the box. This is a 32-channel logic analyzer from lshop.eu. I will link it below. And this is a D-latch that I built. And this is a fairly simple circuit. It's got two buttons and two LEDs on the output. You can see the LEDs on the left side that they will turn on when I press the buttons. So it's very similar to this circuit, but this time it's a little bit more complex since we added some NAND gates. So let's power this up. Okay, so we got the Q output on, and let's see what we can do to turn it off. Normally we would need a falling edge on the clock without having logic high on the data input. So let's see if that works. It looks like it does. I can clock in whatever I want. Well, let's see what it looks like on the logic analyzer output. So I'm gonna press this button here. Oh, it's capturing. Okay. I'm just gonna press some random keys, and then we're going to examine what we have. It's pretty obvious what happens here if we take a look at the signals. The Q output takes the value of the data input, but only at every falling edge on the clock or enable input. Having seen that, we could argue that we do indeed have one bit of memory in our hands. We can cascade these to build a counter, and we can clog them together to build a 4-bit latch. We just need to find a solution that doesn't require 48 NAND gates. 74LS74 is a possible solution. It has two latches in a 1-DIP14 package, so we can use two of these to build the two circuits, a 4-bit latch and a 4-bit counter. In the next episode, we're going to see how these two functions are combined in the 74LS193, which is the core part of our program counter.